Okay, let's give you guys some more practice. So find the radius of convergence and the interval of convergence for this power series. So press pause and have a go. Okay, so to do this, we're going to use the ratio test. So when it comes to the ratio test, you always need to compute this value, an plus 1 divided by an. So this is your an plus 1, and this is your an. So when it comes to the ratio test, you always need to compute this value here. Well, this is your an plus 1, this is your an. Because you're taking the absolute here, you can pretty much ignore this -1 plus -1 minus -1 and so on. All that this block is doing is -1 plus 1 minus 1 plus 1 and so on. So because you're taking the absolute here, you can ignore these two blocks. Okay, so this whole thing here will then become this. You would then group all the n's together. So group all the n's together and then group all the x's together. But visualize this as x to the power of n times x. So this is n plus 1, n plus 1. So this whole thing here will then become this. Now remember, n is moving from 1 to infinity. So n is always positive. N is always positive. This will always be positive. This will always be positive. The whole thing is always positive. So you don't actually need the absolute for this bit here. You don't actually need the absolute here. So you can actually take the absolute. You can actually take the whole thing out of the absolute. So that will then give you this, and then concentrate on taking the absolute of what's in here. Well, cancel these two out. That will just leave you with x. So that will just leave you with absolute value of x. So this whole thing here will then become this. So when it comes to the ratio test, this whole thing here, when it comes to the ratio test, we always need to compute this value here. Well, if this value here is less than 1, then we know it's going to converge. If it's greater than 1, we know it's going to diverge. If it equals 1, then it's inconclusive. Well, if this thing here is equal to this thing, if we want the series to converge, we want this whole thing here to be less than 1. So we require this to be less than 1. But then if you look at this, as n tends to infinity, if you multiply this out, it would be n squared plus 2n plus 1. Well, we don't care about this. The highest term is this. So as n tends to infinity, you've got n squared in the numerator and n squared on the denominator. So the limit here will be 1. So for this whole thing here to converge, we require the whole thing to be less than 1. Well, because this thing here is heading towards 1, then just concentrate on making this to be less than 1. So for convergence, we require absolute value of x to be less than 1. If absolute value of x here, if this thing here is less than 1, then the whole thing here will be less than 1. So for convergence, we require absolute value of x to be less than 1. That means that while looking at this, the radius of convergence here is 1, and the intervals is well, anything in between, anything strictly greater than -1 and strictly less than 1, we know is going to converge. But that on -1, if you put it into here, that on -1, this whole thing here will be equal to 1. Well, whenever this value here equals 1, then it's inconclusive. If you put 1 into here, then this whole thing here will also be equal to 1. Again, it's inconclusive. So it's inconclusive at precisely -1. It's inconclusive at 1. Anything in between, we know is going to converge, but it's inconclusive at -1. And it's inconclusive at 1. So we need to manually check at -1, and we need to manually check at +1. So when x is -1, look at the original power series, and then put this into here and manually check if the whole series will converge. Well, if you put this into here, that will then give you this. Now we need to manually check if this thing here will converge or if it will diverge. Well, merge these two together. That will then give you 1. So, well, this whole thing here becomes this. Now, well, you can see that by the nth term test, in order for any series to converge, the limit must be zero. Well, if you look at this n squared, looks something like this, and then here you're you you're at, in order for any series to converge, the limit as n heads towards infinity must be zero. Well, we know this is going to diverge because it's just getting bigger and bigger and bigger and bigger. This series is going to diverge. So we know that when x equals -1, the series will diverge. So now check when n equals +1. So when x equals +1, put it into here. That will then give you this, and then tidy this whole thing up. It will then become this. So this is in order. Well, when you look at this here, in order for any series to converge, the limits must head towards zero. Here, what you've got is this thing here. Hang on, positive x squared here. So here you've got one. Well, you've got something like this here. So this is positive, negative, positive, negative, positive. You know that this is going to diverge. This will diverge. You should by now recognize that this is going to diverge. So overall, when x equals -1, we know it's going to diverge. When x equals +1, it's going to diverge. So our radius of convergence is 1, centered at 0, and the interval will be strictly greater than -1 and strictly less than +1. But if it's dead on 1, it's going to diverge. If it's dead on -1, it's going to diverge. So anything in between the series will converge. Okay.